In a previous video that I called Rigid Body Motion, and the Dzhanibekov Effect, I gave an intuitive explanation of the Dzhanibekov Effect using the example of a rigid body that consists of two large masses and two small masses connected by struts at right angles like this and in a plane. And the Dzhanibekov effect occurs when you rotate this body about an axis that almost lines up with the principal axis of rotation that contains the intermediate value of the moment of inertia. So for this body, it's an axis close to this red strut. Now, in this video, what I'd like to do is describe the mathematics that I used to analyze this and to create the simulations that I showed. Now, there are a lot of different ways that you can analyze rigid body motion mathematically, and correspondingly, there's lots of different ways you can write computer codes to simulate rigid body motion. One way is to focus on the orthogonal matrix that defines the orientation of the body. You can write a differential equation and integrate that forward in time. So one way is based on the orientation, or sometimes called the rotation matrix. You can also define the orientation of the body in terms of Euler angles. So you can write down a Lagrangian for the body in terms of Euler angles, derive the equations of motion that way, and then solve them numerically. There are other ways, for example, Cayley-Klein parameters. Yet another way that I believe is used for physics engines in the computer gaming industry is based on quaternions. But what I decided to do for this project was to describe the rigid body motion in a different way, because what I was interested in doing is not just analyzing the motion of the body, but also understanding the forces that the struts exert on the masses at the ends. And I found that actually very useful in coming up with an intuitive understanding of the Dzhanibekov effect. So let me describe now how that was done. So we're going to use the method of Lagrange multipliers. And to begin with, we think of the four particles as moving independently. So let's call this particle has mass 1, m1. This particle also has mass m1. The other two particles have masses m2 and m2. And these four particles move in three-dimensional space. So here's our coordinate axes. This is the position vector for the first small particle. Let's call this x1 vector A. And I'll use the A to distinguish it from this particle, which also has mass m1. This is x1b vector. And likewise, this is x2a vector, and this is x2b vector. All right, so we first just write down the Lagrangian for this four-particle system, and then we'll constrain the four particles with the struts, constrain them to lie in the cross pattern. Okay, so the Lagrangian for these four particles, we have, for the first particle, we have 1/2 m1 x1a vector dot. I use dot to denote time derivative. It's the squared magnitude of this velocity vector, plus 1/2 m1 x1b vector dot, magnitude squared, plus for the two larger particles, m2 x2a vector dot squared, and 1/2 m2 x2b vector dot squared. So there's the Lagrangian for the four free particles. Now the particles aren't really free, they're constrained. So what are the constraints? First of all, by the way, how many degrees of freedom do we have here? We have each of these particles can move in 3 dimensions, so that's 3 plus 3, 3, 3. That's 12 degrees of freedom. And now for the constraints. First of all, each of these particles is constrained to be a fixed distance from the origin where the struts cross. We'll take that to be the origin. Okay, and we'll let the length of each strut be 2 times r. So this distance from the origin to each of the masses is capital R. Okay, so we have 4 constraints, namely that the magnitude of each of these position vectors should be equal to capital R. So this is x1b equals x2a equals x2b equals R. So these 4 constraints tell us that the 4 masses must move on the surface of a sphere of radius capital R. Let me draw the masses again. So this is the mass 1a, this is the mass 1b, here's the mass 2b and 2a. Now, these 4 masses must stay at right angles to one another, and of course they must all lie in the same plane. So let's add the constraint x1b equals minus x1a. That tells us that 1b is opposite across the origin from 1a, and likewise x2b lies across the origin from x2a. Now, with this constraint, if we know that x1a has magnitude r, then this tells us that x1b also must have magnitude r, so we actually don't need to impose this constraint. Likewise, we don't need this constraint if we're going to include these 2. So with this set of constraints, we have a body that we have 2 struts holding these 4 masses at a fixed distance r from the origin, but we still don't know that the struts are at right angles from one another, so we need to impose another condition that says x1a and x2a are orthogonal. All right, so this is our complete set of constraints, and let's do the counting here. We have this equals r, that's 2 constraints. These are 2 vector relations, so that's 3 more, and 1 more constraint here. So 2, 3, 4, 5, 6, 7, 8, 9 constraints. And we started with 12 degrees of freedom, so that leaves us with 3 degrees of freedom. Which is the correct number of degrees of freedom for a rigid body with 1 point fixed. Now, as usual with a dynamical system, we can impose the constraints using Lagrange multipliers, or we can impose them with our choice of dynamical variables. And what I'm going to do is a mixture. I'm going to impose these 2 constraints with my choice of dynamical variables, and then let the remaining 1, 2, 3 constraints be imposed with Lagrange multipliers. So these constraints are imposed by letting x1a be simply x1 and x1b be minus x1, and likewise x2a will denote x2 and x2b is minus x2. Then the Lagrangian has this form. This is the kinetic energy term for the particle 1a. This is the kinetic energy term for particle 1b. Here's particle 2a, particle 2b. And then we have our Lagrange multipliers times constraints. So this is the constraint that the magnitude of x1 is capital R, and I've written it as the magnitude squared equals r squared. Likewise, the magnitude squared of x2 is r squared, and x1 vector and x2 vector are orthogonal. The Lagrange multipliers I'm calling lambda 1, lambda 2, and gamma. Of course, we can simplify this by combining these two terms since the minus sign goes away when we square this. Similarly, we can combine these two terms. So the Lagrangian becomes m1 times x1 vector dot x1 vector dot plus m2 x2 vector dot x2 vector dot plus lambda 1 times x1 vector dot x1 vector minus r squared plus lambda 2 times x2 vector dot x2 vector minus r squared plus gamma times x1 vector dot x2 vector. Now the action is just the integral of the Lagrangian, so that's a functional of x1, x2, and the Lagrange multipliers lambda 1, lambda 2, and gamma. It's equal to the integral of L from some initial time, t prime, to some final time, say t double prime. Now the equations of motion are just the statements that the functional derivatives of S with respect to the dynamical variables vanish. So first, the functional derivative of S with respect to x1 vector equals, from this term we have minus 2 m1 x1 vector double dot. From this term we have 2 lambda 1 times x1 vector, and from this term we have plus gamma times x2 vector. Likewise, when we extremize the action with respect to x2, we have minus 2 m2 x2 vector double dot plus 2 lambda 2 times x2 vector plus gamma times x1 vector. And now we extremize the action with respect to the Lagrange multipliers. So this is x1 vector dot x1 vector minus r squared. We also have delta s delta lambda 2 equals x2 vector dot x2 vector minus r squared. And finally, delta s by delta gamma is x1 vector dot x2 vector. So these are our equations of motion. So how do we solve these? Well, the procedure is always basically the same when you have a constrained system like this. The idea is that you differentiate the constraint equations, these three equations, differentiate them in time twice. So that will give equations involving second time derivatives of x1 and x2. Then you use these equations to eliminate x1 double dot and x2 double dot in favor of terms involving the Lagrange multipliers. And then you take those three equations and you solve them algebraically for the three Lagrange multipliers. Then substitute that back into these equations, and what you're left with then is differential equations for x1 and x2 alone without any Lagrange multipliers. Right, so let's do that. First, we differentiate these three constraints. We'll differentiate them once in time and then again. So the first derivative of this equation is x1 vector dot x1 vector dot. Derivative of r squared is, of course, 0. Derivative of this gives 0 equals x2 dot x2 vector dot. And the derivative of this equation is x1 vector dot x2 vector dot plus x1 vector dot x2 vector. Now we'll take a second derivative of these equations. So for this equation we'll have x1 vector dot x1 vector double dot plus x1 vector dot squared, or x1 vector dot with itself. For this equation we'll have x2 dot x2 double dot plus x2 vector dot squared. And finally, for this equation, we have, taking another time derivative, we have x1 vector dotted with x2 vector double dot plus x1 vector double dot dotted with x2 vector, and then there's a term x1 dot with x2 dot and another one here. So we have two x1 vector dot product with x2 vector dot. All right, so there's our constraint equations differentiated twice in time. And now we'll use these equations. This first one tells us that x1 double dot equals, let's see, if I bring this to the left, I'll have a factor of 2m that I divide through. So this is 2 lambda 1 over 2m. So that will be lambda 1 over 2 over m 1 times x1 vector. Let me remind myself here. And then we have plus gamma divided by 2m1 times x2 vector. And likewise, we have the equation x2 double dot is equal to lambda 2 over m2 times x2 vector plus gamma over 2m2 times x1 vector. So we'll use these two equations to simplify our second time derivative constraint equations. So this first one, this will become 0 equals x1 dot product with this expression, lambda 1 over m1 x1 vector plus gamma over 2m1 x2 vector plus x1 vector dot with x1 vector dot. Okay, now you see here we have x1 vector dotted product with x1 vector, but we know that's equal to r squared. We also know the x1 vector dotted with x2 vector is 0. So this dot product with this vanishes. So this equation simplifies to lambda 1 over m1 times r squared from this term plus 0 plus x1 vector dot dotted with x1 vector dot. Now I'm getting kind of tired of writing all these x1 vector dots and so forth, so let me use a slightly simplified notation. Let v1 vector be x1 vector dot, v2 vector be shorthand for x2 vector dot, and so forth, v for velocity. All right, and with that notation then we can see that the solution here for lambda 1 is minus m1 over capital R squared times v1 vector dot with v1 vector, so that's just v1 squared. And likewise, if we simplify this equation using this expression for x2 double dot, we find lambda 2 is equal to minus m2 over r squared times v2 squared. And finally, we want to simplify this equation using these results. Okay, so we have 0 equals x1 dotted with x2 double dot. So the x1 with the x2 gives 0. x1 dotted with x1 is just capital R squared. So this first term gives gamma over 2m2 times capital R squared. And from the second term, here we'll have x2 dotted with x1 double dot. The x2 with x1 goes to 0. x2 with x2 is capital R squared, so this is gamma over 2m1 times capital R squared. And then finally, this third term is just what I'm now calling v1 dotted with v2. and that's all equal to 0. So here now we can solve for gamma. So we find gamma divided by 2 times r squared times 1 over m1 plus 1 over m2 equals minus 2v1 dot v2, or gamma is equal to 2 over r squared and a minus sign, and there's another factor of 2, and then the inverse of this is m1 m2 over m1 plus m2. So this is, just simplify that a bit, that's minus 4 v1 dot v2 divided by r squared times m1 m2 over m1 plus m2. So now we have explicit results for our Lagrange multipliers, gamma, lambda 1, and lambda 2. So we can go back and use those in our equations of motion for x1 double dot and x2 double dot. So first we have x1 double dot equals lambda 1 over m1 times x1 vector. So let's write that down. x1 vector double dot equals lambda 1 over m1, but lambda 1 was minus m1 over r squared v1 squared times v1 squared. And all of that, if we look back at our equation of motion, here it's times x1 vector. Then we have plus gamma over 2m1 times x2 vector. So plus gamma over 2m1 times gamma, that's minus 4 v1 v2 divided by r squared times m1 m2 over m1 plus m2, all of that times x2 vector. Okay, so simplifying this, m1's cancel, we have minus v1 squared over r squared times x1 vector minus 4 over 2 is leaves us with a 2 times v1 dot v2 divided by r squared times m1's cancel, so that leaves us with m2 divided by the total mass m1 plus m2 times x2 vector. Now I'd like to rewrite this in another way using the notation hat for unit vectors. So x1 vector has magnitude capital R, and it's in what I'll call the x1 hat direction. So this is equal to minus v1 squared over capital R times x1 hat. And here we have minus v1 dot v2 over R times m2 over m1 plus m2 times x2 hat. And likewise, if we go through the algebra for x2 vector double dot, it's not hard to guess that the answer is just the same as this, but with 1s and 2s swapped. So this is x2 vector double dot equals minus v2 squared over r times x2 hat minus 2 v1 dot v2 over capital R times m1 divided by m1 plus m2 times x1 hat. Now, of course, this is just the form of Newton's second law. This is the acceleration of mass number 1, and so on the right-hand side we have the force per unit mass on mass number 1. This is the force per unit mass on mass number 2. So explicitly we have the force on m1 is equal to minus m1 v1 squared over capital R in the x1 hat direction minus 2 v1 dot v2 over R times m1 m2 over m1 plus m2 in the x2 hat direction. And likewise, the force on m2 is equal to minus m2 v2 squared over R in the x2 hat direction minus 2v1 dot v2 over r m1 m2 over m1 plus m2 x1 hat. So the picture here is, here's m1, here's m2. Of course, there's also an m1 down here and an m2 over here. And the force on m1 has two components. It has a component in the x1 hat direction, which is just the centripetal force required to keep this mass on the sphere of radius capital R. So that's mv squared over r. And then there's also a component tangent to the sphere in the x2 hat direction. And likewise, the force on m2 has a radial component that's just the centripetal force required to keep this on the sphere. And then there's a tangential component in the x1 hat direction. And notice these two components have the same magnitude. That's just a statement of Newton's third law. The tangential component of the force that m1 exerts on m2 is equal to the tangential component of the force that m2 exerts on m1, with the non-tangential components, the radial components, being absorbed by these other terms, the centrifugal terms. So these are the actual equations that are solved numerically in the computer code that I used to make the simulations for the video rigid body motion and the Dzhanibekov effect. And they're integrated forward in time using a fourth order Runge-Kutta scheme. And you can take a look at the code at glowscript.org. So it's written in Glowscript. And I'll put a link below to the exact folder where you can find this code. And of course, you're welcome to make a copy of the code and to play with it. Now, there are a couple of further questions I'd like to address. In particular, how do we compute the angular momentum and angular velocity for this rigid body? Well, the angular momentum is straightforward. It's just the sum over all the masses in the body of the position vector cross product with the momentum vector. So for the first small mass, we have x1 vector cross the momentum, which is m1 times v1 vector. So this is for the mass that I originally called 1A. And for the mass 1B, we have m1 times its position vector is minus x1, and its velocity vector is minus v1. So this is for the mass that I called 1B. And for the two larger masses, we have m2 x2 vector cross v2 vector and m2 minus x2 vector cross minus v2 vector. And so this just simplifies to 2 m1 x1 vector cross v1 vector plus 2 m2 x2 vector cross v2 vector. This is how the angular momentum is computed in the code. Now what about the angular velocity? Well, recall that the angular velocity is a vector omega, such that for any point in the body, the velocity of that point, just call it v, is equal to omega cross r for any point in the body. So for the smaller masses, we have v1 equals omega cross x1 vector, and for the larger masses, we have v2 equals omega cross x2 vector. And of course, this equation applies to both of the smaller masses, 1a and 1b, this equation for both 2a and 2b. Now, we can also define a vector, let's call it z, as x1 cross x2. So if we remind ourselves of the picture here, here's the two smaller masses, the two larger masses. And x1 vector is the vector from here to here, x2 vector from here to here, so x1 cross x2 is a vector that's perpendicular to the plane of these masses. Now this vector, we can imagine a massless point here that moves along with the body, so in that sense it's a part of the rigid body. So this vector also should satisfy the general expression for the angular velocity. In other words, z vector dot is equal to omega cross z vector. And z vector dot, of course, is just can be computed from the time derivative here. That's v1 cross x2 vector plus x1 cross v2. So now the plan is to use these three equations to solve for omega. So how do we do that? First, let's examine cross product of this equation with x1 vector. So let's compute x1 vector cross v1. That's x1 vector cross omega cross x1 vector. And now using the identity for a triple cross product, this is equal to the dot product of this with this. That's x1 dot x1 times the second vector plus the dot product of this vector with this vector times this vector. Okay, now x1 dot x1 is just, of course, r squared. And here we can rewrite this term in terms of the x1 hat. So we can pull a factor of capital R out of each of these x1 vectors and write this as r squared times x1 hat dot omega times x1 hat. Okay, now we can do the same thing for these other two equations. First of all, for the v2 equation, we have x2 cross v2 equals r squared times omega plus r squared times x2 hat dot omega x2 hat. And for the z equation, we have z cross z dot, that's z cross omega cross z, and again using the identity, this is z dot z times omega plus z dot omega times z. Now what is z dot z? Well, if you look back at the definition of z, x1 is just r times x1 hat. This is r times x2 hat. So z is just r squared times the cross product of two unit vectors that are orthogonal. So it's r squared times what we'll call z hat. So we'll use z equals r squared times z hat. And then that tells us that z cross with z dot is equal to r squared times z hat dotted with itself. So that's r to the fourth times omega. And here if we pull out an r squared from each of these, we have r to the fourth times z hat dot omega times z hat. Now let's combine these three equations, here, here, and this equation. In particular, let's divide by the appropriate factor of r and then add these three equations together. So from the first equation we have x1 cross v1 divided by r squared, and the second equation is x2 cross v2 divided by r squared, and z cross z dot divided by r to the fourth. That will equal omega plus x1 hat dot omega times x1 hat from this equation From here we have omega plus x2, that's x2 hat, dot with omega times x2 hat. And from here we have omega plus z hat dot omega times z hat. So simplifying this, we have 3 times omega plus x1 hat dot omega times x1 hat plus x2 hat dot omega times x2 hat plus z hat omega times z hat. Now x1 hat, x2 hat, and z hat are orthogonal unit vectors, so you can see that these 3 terms is just another way of writing omega. So this is the projection of omega in the x1 direction times x1 hat and so forth. So this all simplifies to 2 times omega. And now we can see how to compute omega as 1/2 of this expression. So let me write that out. We have omega equals 1/2 of x1 cross v1 over r squared plus x2 cross v2 over r squared plus z cross z dot over r to the 4th, where z is defined as x1 cross x2 and z dot is defined as v1 cross x2 plus x1 cross v2. So this is how the angular velocity is computed in the code. So again, you're welcome to play with this code at glowscript.org, and I'll put a link in the description below.